Hey guys, Amanda here. Time for a boring diagram explanation number 9. These models represent the earth science phenomenon of the sun's path in seasons, which is found in topic 4. So, seasons are caused by the tilt of Earth's axis, the revolution around the sun, and parallelism of Earth's axis. Okay. So, something to know about these is when the path hits directly east and directly west, as this one does, September 23rd. The September 23rd is going to be the autumnal equinox. When the path lands north of east and west, that means this is the summer solstice. And when they're south of east and west, it's going to be the winter solstice. Something to know about the equinoxes is they both land on the same place on the map. So the autumnal equinox can also be the same path as the vernal equinox. Okay. So something to do with the sun's path is also shadows. Shadows are longest on December 21st, which is the winter solstice, because the angle of isolation will be lower. Shadows will be shortest on June 21st, because the angle of isolation will be higher. Okay. So, on this diagram, we see the sun's noon position, which is obviously sun's noon position at noon. But we can also infer from it being north of east and west that it's also, this is the summer solstice. So now we can, using this point, we can draw the other two paths of the sun. So how we would do that is decreasing by 23.5 degrees, because that's the tilt of Earth's axis. Okay, so we can see that this is 60, 61, 62, 63. This is 63 degrees. So 63 degrees at the summer solstice. So we would subtract 23.5 degrees from 63. So convert this to 0.5. It's going to be 39.5 degrees. So we would find that on the left side. We would go to that on the left side because this is obviously the northern hemisphere for the way that the curve bends. So 39.5 degrees. So that's where this is going to land, that point. So you would connect it from exactly due east, which is exactly on east, to exactly due west. And then you do that one more time, but you use 39.5 and subtract 23.5. So 23.5. These are all degrees. That's going to be 16 degrees. So you would find 16 degrees. You would mark your spots where you want to put the ends south of east and west. So it says north and south, so this side's obviously the south. So you would connect these 3 dots, and then there you go. So this point will be the equinoxes, and then this point will be the winter solstice. Okay. So, as you see, point A over here, point A is going to be roughly 3 p.m. This is because if this is the path of during the daytime from sunrise to sunset over here. I spelled sunset wrong. Okay. From sunrise to sunset, and this is noontime, we approximate it that over here, these points that hit the horizon are 6 a.m. for sunrise and 6 p.m. for sunset. So roughly, this would be about 3 p.m. Okay. So, this is gonna be a big diagram. So follow along with me. So the summer solstice. So the summer solstice. The autumnal equinox. And the winter solstice. And then the vernal equinox. Okay. So, these will be the names of all of your times. And then the dates for the summer solstice, it's going to be 6/21. For the autumnal equinox, it's 9/23. For the winter solstice, it's 12/21. And then the vernal equinox is 3/21. So, these all occur when the angle of isolation hits directly at a certain point. So for the summer solstice, that lands on 23.5 degrees north, also known as the Tropic of Cancer that you can find on your Earth Science reference table. During the autumnal equinox, it's 0 degrees, which is also the equator. And then for the winter solstice, it's 23.5 degrees south, and that's going to be the Tropic of Capricorn. And then for the vernal equinox, it's 0 degrees again. So during these times, they have different amount of hours of day and night. So, during the summer, for the summer solstice, there are 15 hours in the day and 9 hours at night. During the autumnal equinox, there's 12 hours in the day and 12 hours at night, because it's an equinox, so there are equal hours. During the winter solstice, there are 9 hours of daytime and 15 hours of nighttime, so it's the inverse of the summer solstice. Then the vernal equinox is 12 hours of daylight and 12 hours of night, which is going to be the same as the autumnal equinox because they both land on the same point as their direct angle of isolation. So some other things to know is vertical ray. The vertical ray is the angle that the sun hits at a certain latitude. So, it's also obvious to anyone who lives in the northern hemisphere that the summer solstice is going to be the warmest. So, as we can tell from this graph, it moves. So from there to there, it's 23.5 degrees, because that's the tilt of the Earth's axis. And then from here to here, it also moves 23.5 degrees. So, as I said, this side will be rise, as in sunrise, and this side will be set, as in sunset. So we can also tell that this little quadrant is north of east, then this is south of east, then this should be north of west, and then this will be south of west. So that might help you. It might help you if you fill that out, so you can tell where you were supposed to line up the apparent path, which we did here, which we also labeled. So sometimes on these graphs, they give you Polaris, which is the star that never seems to move in the night sky. So, you see Polaris. When you see Polaris, the angle that you see it at is the same as your latitude. So, the angle of view equals your latitude. So sometimes they give that to you on one of these graphs on an area such as this. So pretend that Polaris is at 40 degrees. That means your latitude is going to be 40 degrees north. And we know it's north because of the way that the sun's apparent path bends. Since it bends this way, that means we know it's the northern hemisphere. If it was going the other way, we would know it's the southern hemisphere. Okay. This was the boring diagram explanation number 9 for topic 4 for seasons and sun's path. Thank you.